in Moscow, and we continue our remote sensing seminar focused on river sediments. And today we'll go to the sea. We'll have some next step from river to the sea. And my name is, My name is Alexander Osadchiev. I work in Moscow in Shershov Oceanology Institute, and I deal with river discharge in coastal sea areas. And today I will give you a presentation about what happens with river discharge in the coastal sea, what happens with river sediments, and how can we study these processes of spreading of suspended sediments coming from river to the sea using satellite data and numerical modeling. So I will start with my presentation. Okay, here we go. Satellite monitoring and numerical modeling of river-borne sediments in coastal sea. So the general concept of what we are studying, what we are talking about today, is river plume. So when river inflows to the sea, riverine water is fresh water, it is low saline water, or even almost zero saline water, and as a result, it's less dense than the seawater. And when river inflows to the sea, this less dense riverine water forms a very thin layer on the surface of the seawater. And this thin layer is called river plume. Very often, very often, rivers are much more turbid than coastal sea. And you can easily detect this river plume on satellite images, on aerial images, from the plane, from anywhere, from the top. And even if you are standing on the seashore, you can see how blue and not turbid marine waters, they are nearby, and very turbid brown river plume water. And that gives us opportunity to study river plumes very well because they are easily detectable from saline seawater. So here you see different river plumes in different parts of the world, and you can see that they have very complex shape and they are very different, and we will speak about that today. So the key difference, so when we look on river plume from the marine point of view, we speak about them and we study them as individual water masses, because riverine water, when it is in the sea, it's very different from ambient seawater. Firstly, because it's low saline and it has large buoyancy, and this buoyancy puts river plumes on the surface and makes them very thin. So salinity is the main characteristic that is used to distinguish riverine water, river plume water, and sea water. But very often we focus not on salinity, but on turbidity, because we see turbidity from space much better, with much more better quality, better accuracy than salinity. So when river inflows to the sea, after the riverine water exits the river estuary, at some point, at some lift point, it loses its connection with the river bottom and sea bottom, and it goes up and forms this surface advected river plume, which mixes a lot with seawater. And here is some principal scheme of formation of river plume after it exits, after river flow exits the estuary. If there is no external forcing on the river plume, if there is no tides, no sea currents, and no wind forcing, actually wind forcing is the most important forcing which affects river plume, surprisingly, not marine currents, but wind forcing. But we'll speak about that a little bit later. So if there is no external forcing, river plume experiences only Coriolis force, because our planet is rotating, and many processes in the sea, they are like slow enough to be affected by the Coriolis force. And as a result, you can see at this slide what happens with the river plume if there is no wind, tide, and coastal current. So the river forms some area, quite big area, adjacent to the river mouth, and then there is some circulation, anticyclonic circulation near the river estuary in this river plume, and then it forms a coastal current eventually. So there is some transit zone near the estuary, and then it forms a coastal current, which is in a geostrophic balance, and it goes to the right in the northern hemisphere and goes to the left in the southern hemisphere. So the ultimate phase of river discharge of river-borne sediments as well, which inflows to the sea from rivers, is to be transported along the coast to the right in the northern hemisphere, or to the left from the river mouth in the southern hemisphere. And this law works a lot. So it's very important law about this, the influence of the Coriolis force on river plumes. So that scheme was useful for river plumes which experience like some ideal river plume which experiences no external forcing. But river plumes are very different, and they're very sensible to wind forcing, to coastal circulation, to variation in discharge rate, in river discharge rate, to tides, to waves. Waves also provides mixing of river plumes, to ambient stratification of coastal area, and these are external forcing conditions with which affects strongly area, shape, and position, and even presence of river plume. Because if there is a very strong mixing and river is not so big, the river plume can even not be formed, because it will be very quickly mixed with saline seawater and not form any surface advected, some surface advected layer. So also there are there are a certain number of characteristics, morphological characteristics of shoreline, of position of river mouths, and of bathymetry of coastal sea, which affects dynamics of river plumes. And when you have estuarine river, deep estuarine river, there is one case. When you have deltaic river, it's another case. The angle of inflow of river to the sea also affects the formation of the river plume. And latitude, of course, so Coriolis force, it is very small on the equator, even zero on the equator, while it increases greatly at the poles. There are no rivers on the poles, but there are rivers in the moderate latitudes, which experience strong Coriolis force. So there are many external conditions which makes the great variety of types of river plumes, of their dynamics, and that makes them quite a complex field to study. So again, what we need this slide. So it's another one text slide without any pictures, but we need this slide because we want to model river plumes. And in some case, it is more easy to model a river plume than to model the circulation in the sea, general circulation in the sea. So the river plume is surface advected mostly, and it's like the surface layer, and you have to simulate, you have to calculate only forces which affect the plume in the surface. And these forces are pressure gradient, because river plumes are surface advected and they have smaller density, less dense than ambient sea. That's why there is pressure gradient formed by horizontal density gradients. Also, there is Coriolis force, which affect river plume, and there is lots of friction. It is friction on the surface between the river plume and the air, which is determined by wind forcing. There is friction on the bottom between river plume and subjacent seawater, saline seawater, which also affects spreading of river plume, and it is determined by coastal circulation, sea currents, and also tides. And there is lateral friction, and we have to consider fluid drag because river plume, they stay consolidated. And also there are according to this according to this momentum budget, according to these forces which affect spreading of river plume, we have to once we want to model a river plume, we want to get some data about river discharge, which forms the plume, about wind stress and ambient circulation and tidal circulation, which also affects dynamics and mixing of the plume. And finally, what is also important when you think about river plume, when you study river plume, when you make in situ measurements, or when you want to model the river plume, is that the river plume doesn't expand constantly. So it doesn't it mixes with seawater. So there is a certain volume of river water which constantly inflows to the plume from the river, but also there is a certain volume which is mixed, like mixed and removed from the plume as a result of mixing between the plume and the seawater. And when these volumes are equal, so you receive to the plume the same freshwater volume which is mixed out of the plume, then the plume is stable. And also we have to model mixing, and we have to reproduce mixing of the river plume and seawater, and we have to deal with mixing budget, and it's also depend on some turbulent flux between river plume and seawater. So let's move to satellite remote sensing of river plumes. So river plumes are very different from surrounding ocean. And what is important that there are many parameters, characteristics which can be used to distinguish river plume from marine water, from seawater. And let's talk briefly about what kind of satellite products could be used to study river plumes to distinguish them at satellite data. So first, we should start from salinity, because salinity is the key feature. Low salinity is the key feature of river plumes, and there are satellite salinity products which becomes better, which are now developed very quickly, and satellite salinity is a perfect feature to study river plumes, but only for large ones, because spatial resolution of satellite salinity is quite large. It's like several dozens of kilometers. So we can easily detect large river plumes, for example, the Obienise and Lena plume formed in the Arctic Ocean, which spatial extents are hundreds of kilometers. And for these big plumes, or for Amazon plume, or for Mississippi plume, satellite salinity works very well. but for smaller plumes, it's not useful. Also because satellite salinity works not so well near the coast, and you see at this picture that near the coast you will have like white blank areas not covered by satellite salinity. So what is also important characteristic of in the sea, so it's salinity and temperature. And surface temperature is also very useful to study river plumes, and it is also very useful for studying small plumes. And we have satellite temperature products from Landsat, from Sentinel-3, which are available and which are free. And very often we can detect river plumes at satellite temperature products. But satellite temperature, surface temperature, should be used with caution because very often temperature of rivers is different from temperature of sea. When rivers flow from, for example, here we see the Russian Black Sea coast, and we can see two cold plumes because the Black Sea is quite warm sea, but the plumes are formed by rivers which are fed by mountain snow, and that's why rivers are cold. But sometimes rivers are colder than sea. Sometimes rivers are warmer than sea, and you can see warm plumes and satellite temperature images. But sometimes rivers have the same temperature, and you can see nothing. You cannot see river plumes in the sea. And also the problem of these satellite temperature products are that they depend on cloud coverage. So there are cloud limitations, and for certain areas it's important. But there are also passive microwave sea surface temperature, and it is useful for large plumes. Again, if the plume is differs in temperature with ambient sea. And here we can see Mississippi plume, which is this passive microwave doesn't have cloud limitations, and we can get data for every day, and we can detect many plumes using this passive microwave data. Now we move to ocean color, to other products of derivatives of ocean color, such as total suspended measure and chlorophyll concentration or color dissolved organic matter concentration. It's the same. They are even better than temperature, but they also have cloud limitations. But for turbid rivers, usually rivers are turbid. Usually river plumes are also turbid, and usually river plumes have high chlorophyll and dissolved organic matter concentration because of nutrients available in the river water. So these products are very good for study river plumes, but also it could depend on the certain region, and it could not work in some regions. Also, there is radars, satellite radars, synthetic aperture radar, and they also could be used for detection of river plumes. Also, they could be tricky and not work, but sometimes they are very, very, very nice to detect river plumes. And also they don't have cloud limitations. Finally, we can speak about satellite altimetry, which is also available and widely used in ocean science, but it have low spatial resolution, and it can use only for large plumes. And also there are some problems of usage of satellite altimetry because of low accuracy and because of wind. Sometimes it gives misleading results. So new altimetry satellite SWOT hold promise to provide better spatial coverage and better resolution and better accuracy for mapping river plumes. And in it's already available for 1 year of SWOT data. It was launched just a year and something ago, and it's a big question if we could use SWOT for good detection of river plumes. So what we have in total, so what we have for small plumes, in this talk I will provide special attention to small plumes. So for small plumes, we have only sea surface temperature and ocean color and some derivatives of ocean color, which could be used to detect river plumes. So there were lots of text, and now we move again to pictures. So here you can see how we can see the river plumes at total suspended matter satellite product. You see these two plumes in the Black Sea. It's the Russian coast of Black Sea. It's so it's northeastern part of the Black Sea, and these two rivers were detected at the image with sea surface temperature, and now we can see them at total suspended matter concentration. And you see turbid rivers, and you see that they have very different shape. They could be stretched in different directions according to wind forcing. They can be small and can be big, and they have very wide variety of possible shapes and forms and areas. River plumes are often interact with eddies, and it's the same. It's two other rivers at the same Black Sea coast, and you can see on the left eddy chains which capture some parts of some certain water from river plumes and moves this water offshore of the river. And on the right panels, you can see the big eddies formed after the cape, which also captures the plume and changes it in area. So you can see the red dots which indicate these eddy chains and single eddies. And we can detect internal waves in river plumes. It's again the same Black Sea coast, and you can see internal waves which are formed by the inflowing river stream, and they are propagating inside the plume. And what I want to tell you that there are so many complex processes which happen in river plume, which are important to understand if we want to study the interaction of river plume with ambient sea water, if we want to study motion of a river plume, if we want to study mixing of river plume, all these processes. And I just showed you two which are easy to observe because river plume is turbid and it has some specific shape when it interacts with eddies, and it have some specific manifestations of internal waves which increase its mixing with seawater. So in order to study these small-scale processes at small plumes, aerial imagery is very useful. We spoke before about satellite imagery, but if we want to go deeper, if we want to study river plumes deeper and the sediment transport as well, we applied aerial imagery, and aerial imagery provides lots of details as compared to the satellite imagery. You can see the difference. And aerial remote sensing, what is important, it could provide almost continuous detection of position of a plume during daytime when it is sunlight. The problem of satellite imagery is that satellite imagery is just a snapshot, some certain time, day and time, and it doesn't provide any information about dynamics of the plumes. But if you use a quadcopter, if you use aerial remote sensing, you can fix a point on the shore and lift the quadcopter and observe the plume, observe its motion. When the battery is low, you put the copter down, you change the battery, and immediately lift it again. And for this point, for this mechanics, you can provide near continuous aerial observations of a plume during hours and hours and days. And for example, what we studied, so just an example of the study which we provided, which we performed, and which become possible only because of usage of aerial imagery, aerial remote sensing. We calculated the response of a river plume to wind forcing. It's quite a small river plume. The river discharge is about 100 or 150 cubic meters per second. And we wondered how quickly river plume could change its position, could respond to wind forcing when wind direction changes. For example, you can see a series of images, and at the beginning of at the top left image, you can see that river plume is spreading to the right from the river estuary, and then it changes its direction. At the final image, it is right bottom image at 6 p.m. You can see that river plume is now spreading to the left from the river. And we, using this near continuous aerial remote sensing, we could quantify quantify the velocity of the plume and its dependence on the wind velocity. And for this certain plume, we found out that the response of the plume to changes in wind forcing direction is only 15 minutes. So we had meteorological station which was working every minute, measuring the wind data. And once the wind changes its direction, in 15 minutes, the plume changes its spreading direction. It's starting to rotate, starting to adjust to wind forcing. And the same for velocity. Velocity is also quite high. It's just wind velocity divided by 20. So we can see energetic eddies within the plumes, which I was speaking just a few slides before using aerial images. We can see again high frequency internal waves, and all these data could be collected better with aerial remote sensing if it's available. Some features on the plume front, which also affect mixing. So to conclude this part of my talk about satellite and aerial data. Satellite data is very useful. You can detect river plume. You can follow its dynamics, its changes during different days and during different seasons. It could be used with caution. There are different satellite products useful for small plumes and for large plumes. For small plumes, it's better to use sea surface temperature and some optical derived satellite products, and they should be used with caution. So once you want to study spreading of river plume with satellite data, you should find some maybe in situ data or some information about this plume, how it should be, because sometimes you can get misleading results, because for example the ambient sea is also turbid, and you can see like bottom sedimentary suspension, not river plume, which resulted in high turbidity. But generally, for many small river plumes, satellite data is very useful to get some first impression, first information about the plume. And for large plumes, you have to use sea surface salinity mainly, and also radiometer temperature also is useful. But when you want to step in if you want to study river plumes much better with better resolution, spatial and temporal resolution, for small river plumes, aerial imagery is very, very useful. So now we can switch to modeling, and I will just give you a brief information about what can be done in this direction. We created a Lagrangian model of river plume. A Lagrangian model is it's different. There are two types of models, Eulerian and Lagrangian. And Eulerian equations, you have some fixed point of space, and you calculate some features, some characteristics in this point of space. But for Lagrangian equations, you represent motion of a, you move with the parcel. So you have some motion of a parcel of the substance, and you move with this parcel, and you calculate characteristics for this parcel. So we can remember which momentum budget and external forcing conditions which are important for river plume. It's wind, buoyancy force, Coriolis force, and ambient coastal circulation. So we created a numerical model of a river plume, and it is a Lagrangian model, and we represent a river plume as a set of parcels. As far as a river plume is adjacent to sea surface layer, we can make a two-dimensional model. So we think we represent the plume as a water column which is adjacent to sea surface, and it doesn't lose connection with sea surface. So we have a parcel, and what we have, what kind of momentum budget we have for the parcel? We have its velocity; it moves. As a result, we have Coriolis force. We have wind stress, which affects on the top of the parcel according to friction between atmosphere and river plume. We have the same on the plume bottom. We have vertical friction between plume and ambient sea, and we have salinity diffusion. We have mixing, which is provided by friction between river plume and subjacent sea, and we have lateral friction between adjacent parcels because we have some fluid viscosity. And we have pressure gradient force. If we have a parcel which is bigger than nearby parcel, we have horizontal pressure gradient, which provides pressure gradient force. And as a result, we calculate acceleration of the parcel, so we have momentum budget of the parcel. So this is very easy and very simple way to represent and to model a river plume, because river plume it is reproduced as a set of parcels which are moving, and we don't model the ambient sea. We model just motion of these parcels, and it provides very good results at low computational cost. So here are the transport equations, which are also connected with all these forces. There is some mixing budget, which will also make some parameterizations for mixing. And here is an example of how it works. This is also one of the rivers, one of the river plumes at the Russian Black Sea coast. And we calculate motion of the plume according to local wind forcing, according to coastal currents, and according to river discharge. And you see that the response of the river plume on local wind forcing is very quick, and the mixing of a river plume is also very quick when very strong wind forcing. And this is have very good agreement of what we see when we have aerial remote sensing of the plume, how it moves and how it reacts to the wind forcing. And that's another one support for usage of Lagrangian models, for Lagrangian application, Lagrangian way of modeling to model river plumes, because they are very different from ambient sea. Their dynamics are very different from dynamics of ambient sea, and river plumes are like a very thin layer above the sea surface, which have its motion derived by wind forcing mainly, actually. So let's move to sediments. I speak so much about river plumes, but I very rarely mention sediments. But now we are ready to speak about sediments, of riverine sediments, which inflows to the, which are transported to the sea with river water. So using this model, we can also represent motion of sediments. And sediments, their vertical motion is governed by turbidity, and also is governed by gravitational force. And we represent sediments as passive tracers of river plume dynamics in horizontal direction, but on vertical direction we have their motion according to gravitational settling and according to turbulence. And once sediments are inside the plume, they are governed by plume dynamics. Once they settle beneath the plume and get into the ambient sea water, they are governed by coastal sea circulation. So also there are some parameterizations for these processes. And now I can tell you about some applications of this modeling, of spreading of river-borne sediments in coastal sea. We had a project in Taiwan, and we wanted to understand where sediments are accumulated on, where river-borne sediments are accumulated on marine seafloor, after typhoons. There are lots of typhoons in Taiwan, and rivers in Taiwan are very high turbid rivers during typhoons. They have very high sediment concentration. And the problem in Taiwan is that they have submarine landslides. The sediments which are transported from river to sea and accumulated at seafloor, then they form turbid submarine landslides, and they break telecommunication cables at the Taiwan coastal areas. And it was a task to model the areas of accumulation of sediments, the river-borne sediments after typhoon, and to find the possible ways of submarine landslides, and possible ways where possible areas where cables will be broken. So you can see on the right there is accumulation after flooding conditions, and you can see that the scales are different. So it's like several, maybe about 100 times more sediment is accumulated after flooding typhoon conditions on the right as compared to normal conditions on the left. And spatial pattern is also different between normal conditions and flooding conditions with very strong wind forcing on the sea surface. So here is the broken cables, and here is what we resulted from our modeling. So once we have data about river discharge and sediment concentration in the river and wind forcing and tidal circulation and currents, we can model where sediments will be deposited on seafloor, and then how they will form landslides and what will be the trajectories of these landslides. And on the right, on the middle, on the right panel, you can see the green is the areas which could be areas of formation of landslides, and red is the areas of possible propagation, ways of propagation of landslides. This was performed by modeling. river-borne sediments in the sea. Another one case is we return to the Black Sea, and we have many small rivers which inflows to the Black Sea. These are mountainous rivers, and sometimes we have also flooding at these rivers, rain-induced flash flooding conditions, and we have so once we have like in the middle flooding conditions, we have very quick very large inflow of river-borne sediments to coastal sea and its redistribution along the sea. Do you remember that when there is low forcing, ambient forcing to the river plume, it is spreading to the right from river mouths. And we see the same for these small rivers, multiple small rivers in the Black Sea. So they are suspended, their river plumes are forming a longshore current, fresh and alongshore current to the right from river mouths, and the river plumes merges into one big river plume, one big freshened stripe along the coast, directed to the right from the river estuaries, and we have the same direction of suspended sediments, river-borne suspended sediment transport, which we also reconstructed for the Black Sea. Another one case was environmental disaster in Brazil. So we worked with our Brazilian colleagues, and in 2015, they had a problem. They have an environmental disaster when a big volume of ferry slurry at the ferry mine, it was deposited to the river basin, and because of some like reservoir where there was lots of mud after ferry produced by ferry mine, ferro mine, iron mine. Sorry, not ferry, iron mine. Some slurry produced by iron mine inside the Brazil territory. The reservoir was broken, and this slurry inflowed to the river, and then it transported the whole riverway, and then it was inflowed to the sea. And the question was, will this sediment, this iron sediment, will it reach the protected areas, marine protected areas in the sea, in Brazil coastal water? We also modeled that case, and also found out the areas where it will be deposited in the Brazilian seashore using this model. So it's almost 45 minutes of my talk, and I should go to end. So what are the takeaway messages of my talk today? So there are some satellite products which can be used for detection of river plumes at satellite images. And if you have no data, no information, and you just want to get some information about some river plume, about some, actually not river plume, for your case, maybe for spreading of river-borne sediments in the sea, where sediments are deposited. So the first information, the first approximation will be after you look at satellite imagery and you see the area of the plume, the form of the plume, how long is the plume, where it is spreading, and you can get this data for small rivers. You can get this data easily from satellite products, from ocean color products and sea surface temperature. And MODIS, Landsat, and Sentinel are free, and they can be used for this kind of preliminary research. Then, if you want to go deeper about where river-borne sediments will be transported in coastal sea, you should think first about river discharge and wind, because river discharge and wind are the main external forcing conditions that govern river plume dynamics. If you have increase in river discharge, you have increase in plume area. And generally, if you have change in wind direction, you have very quick change of river plume spreading direction. Of course, that is, we speak about small plumes, because large plumes they have different dynamics, and they are much more stable, and it's a different story to speak about large plumes. So we speak about small plumes. So if you want to understand where at this certain day or this certain season the river-borne sediments are transported, in which direction, along the shore or to the open sea, you should look at wind forcing, at the dominating wind forcing direction. If you want to go deeper, and if you have some special river which you have access to, and if you want to study river plumes better, you have to use quadcopters. They are quite cheap, and they're very, very useful to study spreading of some certain river plumes with very high spatial and temporal resolution. And finally, if you want to understand everything about what happens with river-borne sediments in coastal sea, what happens with how transport by river plume is formed, how it changes, you have to use numerical modeling and Lagrangian numerical modeling, and in particular striped numerical model, which was developed by our research group, can provide this opportunity, and you can use numerical modeling to solve wide variety of problems connected with understanding of the fate, transport and fate of river-borne sediments in coastal sea. So thank you for your attention. I'm ready to answer the questions.
Thank you, Alexander, for your lecture. It was, yeah, I really enjoyed. Dear participants, you're welcome to ask your questions in the YouTube chat, and we will share your questions with Alexander. We do have already some questions, Alexander. So the first one is, what is the purpose of using various satellite data to map the river plumes, since they have their own limitation?
The purpose is to compare if there is some river which you do not have access to. You look at sea surface temperature and you see something which could be which you think is a shape of a river plume. You see some feature, some like cold area adjacent to river estuary, and you think maybe it is a river plume. But then you have to look at sea surface at for example sediment concentration to check if it is really a river plume or if it is some other feature which provided cold temperature, for example, coastal upwelling. So once you compare different satellite products, you can be more sure that what you see is indeed a river plume, because the best is salinity, and the only 100% is salinity, because like river is the only source of fresh water in the sea. Also there is rain, but it looks different. Also there's sea ice melting in some areas, but it also looks different. So the main purpose is to be sure that you are not misled by some other processes affected temperature or sediment concentration or chlorophyll or sediment.
Thank you. I think this is a pretty good answer. The second question is, which satellite data is best performed, and what is your recommendation for mapping the river plumes?
My recommendation, for example, you should find the spatial scale. If your plume is less than 1 kilometer wide, for sure you have to use only Sentinel and Landsat, because they provide like several dozens of meters of spatial resolution, and MODIS, which is 250 meters, will not be useful. So for small plumes, about 1 kilometer wide, it is Sentinel and Landsat, and for plumes from 1 kilometer to 10 kilometers, it's better to use MODIS. And if your plume is greater than 10 kilometers, then maybe from 10 to 50, then you should think about sea surface salinity. It's SMAP and SMOS, sea surface salinity. Okay.
Thank you for recommendations. I do have a question for myself, if you don't mind. Do you have any idea how can we estimate the volume of the plume without modeling? Is it possible?
It's a tricky story, and there is no direct relation between plume area and river discharge rate. There is absolutely no direct relation because plume can, especially small plume, it can be easily pressed to the shore, and the same volume could be stored in a deep plume or less deep plume. It could be pressed or it could be spread to the open sea, and there is absolutely no relation, according to my expertise, for both small plumes and for large plumes. We had we published a paper and we made a model in 2015, and that was this question: can we reconstruct river discharge volume from river plume satellite image? And the answer is yes, only if we know external forcing conditions. If we have external forcing, wind forcing and wind forcing, actually wind forcing is enough for small plume. If we have wind forcing, we can model generally we can model spreading of river plume with different discharge and see the similarity. And area of river plume strongly depends of discharge, of course, for fixed wind conditions. If you have fixed wind conditions, the area of plume changes with increase of discharge. And this is the case how we can reconstruct river plume area. So for fixed wind conditions, there is dependence between river volume and river plume area.
Right, thank you. So if I understand you correctly, for example, if I'm interested in suspended sediment discharge of the river, I can either use the surface suspended sediment concentration estimated from the satellite imagery for my estimates, or I can use this external forcing model equation. I'm sorry. Estimate. I'm sorry. Yeah. Estimate suspended sediment discharge based on the current wind conditions.
If you know if you know sediment concentration in the river, then you can this relation which we're speaking about, it's only to river discharge, to freshwater discharge. And if you know concentration in the river of suspended sediments, then of course you can calculate that. But it's better to use both. I think both methods have some inaccuracy, and I think you have to use both to compare them at least. What can I say more about this problem? It is if you know a river well, if you worked on this river, if you know how its behavior, if you know the behavior of a river plume, you can train yourself to get reliable results. But if you want to apply this to some river somewhere you don't know what's going there, it could be misleading. Okay. So you could be cautious. You should be cautious with these procedures.
Okay, fair enough. Thank you. One more question from our participants. So, what is the difference between the settlement of river sediments or plumes in estuaries and deltas you observe? Can be easily distinguished by satellite data or not?
Again, please, the difference of sediments in estuaries and deltas.
Difference between the settlement of river sediments or plumes in estuaries and deltas you observe.
Estuarine rivers, they are much deeper than deltaic rivers. If rivers have the same discharge rate, but one river is estuarine and then the other river is deltaic, the estuarine river will provide deeper river plume, and it will capture the plume is turbid inside. The plume is very thin and very turbid inside. There is a very good mixing inside the plume, vertical circulation inside the plume. And the plume captures, as a result of this turbidity, high turbidity within the plume, it captures fine sediment very well. And it captures it and transports it far from river mouth. And if you have deltaic river and the plume is thin, there is a small vertical distance for a suspended sediment to leave the plume, to fall down and leave the plume. But if the river is estuarine, the plume is deeper, much deeper, and there is a much greater distance for fine sediment to exit the plume. So it will be transported far from river estuary, from river mouth in case of estuarine river as compared to deltaic river. And also what is important, river plumes, individual river plumes, they dynamically interact with each other. And if you have one plume and very close another plume and they merge, they also interact and they change their pathways, spreading pathways. And you have a deltaic river, you have lots of small plumes formed by every deltaic channel, and they all interact with each other, and it makes also very complex circulation scheme, dynamical scheme, and also it prevents transport of fine sediments in surface layer, because this interaction like decreases it decreases the dynamics in the plume. So estuarine rivers, I think they transport fine sediments within the plume at longer distances from river mouth than deltaic rivers.
Okay, thank you very much, Alexander. I'm mindful about time. I think we have only 1 minute left, so thank you very much, Alexander, for giving this lecture. It was really enjoyable talk, and thank you everyone for asking their questions and attending. I just want to remind you that tomorrow we will have a lecture will start a bit later than today. So tomorrow it will begin at 4 p.m. Moscow time, and it will be given by Professor Edgardo Latrubiese about remote sensing of sediments applied to hydrogeomorphic studies in large rivers. So please be aware that the time is a bit different. Apart from that, I'm really happy to close today's session. Have a great evening and mornings.